Okay, let's just dive right in. Have you ever actually stopped to think about how a self-driving car or even one of those robots zipping around a warehouse finds its way from point A to point B without just crashing into everything? Well, it's not magic. It's this absolutely fascinating field called path planning. And today we're going to trace the entire evolutionary journey of how robots learn to navigate their world, starting from the simplest little wall-following bug all the way up to the sophisticated AI brains that are in our cars today. So first up, we'll look at how a robot even builds its own mental map of the world. Then we'll check out the first, kind of simple steps they took before a huge breakthrough idea changed everything: random guessing. From there, we'll dive into how they solve the really tricky problem of narrow passages, how they turn those plans into actual real-world action, and then finally, we'll take a peek over the horizon at the future of robotic navigation. So let's kick things off with the big question, right? How does a machine build this mental map and then figure out a safe route through it? Well, the answer lies in this really clever trick that turns a messy, complicated, real-world problem into what's basically a simple puzzle of connecting the dots. And that trick is called configuration space, or C-space for short. Now, I want you to forget about a simple 2D map. C-space is a much more abstract map of every single possible state the robot can be in. We're talking every joint angle, every rotation, every position. And in this special world, there are only two kinds of places: safe zones, which we call free space, and crash zones, which we call obstacle space. This visual right here simplifies the entire, super complex problem. Path planning really just boils down to this: can you find a continuous line from that green start dot to the red goal dot that stays completely inside the white free space? That's it. That's the whole game. So, how did we first teach robots to even play this game? Well, we started with some incredibly simple, really intuitive ideas. So let's take a look at the foundational algorithms that really started it all. Meet the bug algorithm. And yeah, it's pretty much as simple as it sounds. The robot basically has two rules. Rule 1, go straight toward the goal. Rule 2, if you hit something, just hug the wall and follow it around. It's not elegant, not by a long shot, but for a simple robot with limited sensors and no map, it's a surprisingly decent place to start. Now, the most famous version, Bug 2, refines this a little bit. It moves in a straight line toward the goal, simple enough. When it hits an obstacle, it switches into boundary following mode. But here's the really clever part. It only switches back to heading for the goal when it recrosses its original straight line path at a point that's closer to the goal. It's a simple rule, but it guarantees it won't get stuck walking around the same table leg forever. But let's be real, wall following is not exactly efficient if you actually have a map. So what if you do? Well, an early approach was to turn that map into a grid, kind of like a chessboard. Then you can use a classic search algorithm like breadth first search, or BFS. It just starts at the beginning and explores every single adjacent square, then the neighbors of those squares, and so on and so on. And this is the perfect analogy. BFS literally expands outwards in these perfect layers, just like a ripple from a stone you dropped in a pond. And because it explores level by level, the very first time it touches the goal, you are guaranteed to have found the shortest path, at least in terms of grid steps. The big problem, though? In a huge space, or with a complex robot arm, the number of squares to check becomes astronomically large. It just doesn't scale. So, to solve that massive scaling problem, researchers had this truly revolutionary idea. They thought, what if we just stop trying to check every single point? What if we just throw a bunch of random darts at the map and try to connect the ones that land in safe spots? And this, right here, was the dawn of sampling-based planning. The first big approach here is the Probabilistic RoadMap, or PRM. So the algorithm just scatters thousands of random points, throws out any that land inside an obstacle, and then tries to draw straight lines between nearby points. If a line is clear of obstacles, it becomes a road. You end up with this cool web-like roadmap that you can then search for a path. It's really perfect for static environments, like a factory, because you only have to build this computationally expensive map one time. Okay, but what if you need a path like right now? Well, that's where the rapidly exploring random tree, or RRT, comes into play. So on the left, you see PRM building out that whole network. On the right, RRT works totally differently. It starts at the beginning and grows a tree of paths outwards. It does this by picking a random point and then extending the nearest branch of the tree just a little bit in that direction. It's a method that's naturally biased to rapidly explore open, unknown areas of the map. Now, RT is great at finding a path really quickly, but it's not necessarily the best path. And that's what RT star is for. The secret sauce, the crucial point, is this thing called the rewire operator. So when RRT star adds a new node to its tree, it looks at its neighbors and asks, hey, does connecting through me create a shorter path for any of you guys? If the answer is yes, like you see with that orange dashed line, it literally rewires the tree. And over time, this constant optimization pulls the path tighter and tighter until it gets to the shortest possible route. But standard random sampling has this one giant Achilles heel. It's terrible with narrow passages. I mean, think about it. The odds of a random point just happening to land in a tiny little doorway are super low. So to solve this, roboticists developed a whole toolbox of clever, specialized sampling strategies. First up, we've got Gaussian sampling. The logic here is pretty intuitive. If you're looking for a doorway, you should probably be looking near a wall, right? Well, this method basically mimics that. It samples 2 points that are really close together. If one lands in free space and the other lands inside an obstacle, it keeps the free point. This has the effect of concentrating all the samples right along the boundaries, exactly where you're likely to find a path through a narrow gap. Now, bridge sampling is even more direct. It's designed for one purpose, finding those gaps. It samples 2 points, and if they both fall inside obstacles, it checks the midpoint between them. If that midpoint just happens to be in free space, boom, it keeps the sample. Why? Because it has almost certainly just found a bridge between 2 obstacles. Super clever. And finally, there's visibility sampling. The whole goal here is just efficiency. I mean, why would you add 1,000 redundant points in a big open room? This strategy only adds a new sample if it does one of 2 important things. Either it's in a brand new area that can't see any part of the existing roadmap, or it acts as a crucial link that connects 2 previously separate parts of the map. It keeps the roadmap lean, mean, and fast to search. Okay, so we have this beautiful, perfect line on a map. Great, but how does that actually turn into wheels turning and motors spinning? This is where we shift gears from global planning, which is the overall route, to local planning, which handles the immediate, real-time movements and, avoids that person who just stepped right in front of you. The dynamic window approach, or DWA, is a real workhorse in the space. In every single fraction of a second, the robot imagines a whole set of possible short arcs it could drive. Those are the red and green lines you see. It simulates each one, instantly throws out any that would lead to a collision, and then it scores the safe ones based on things like speed, how far it is from obstacles, and how well it's following the main path. It picks the highest scoring move, executes it, and then immediately repeats the whole process. Another really elegant method is the timed elastic band, or TEB. I want you to literally imagine your planned path is an elastic band. You've got these internal forces pulling it tight, trying to make it short and efficient. But at the exact same time, obstacles are exerting this repulsive force, pushing the band away to keep a safe distance. It's this constant, dynamic balancing act between speed, safety, and smoothness. This field is just moving at an incredible pace. So let's end this by looking at the absolute cutting edge, the algorithms that are pushing robots to be even smarter and even quicker on their feet. Remember RRTX? It was great, but it could be a little slow to find that perfect path. Well, informed RRTX is basically the turbocharged version. Take a look at the diagram. Once it finds any initial path, it stops wasting time sampling the whole map. Instead, it draws that orange ellipse you see around the current best path and focuses all of its new random samples inside that promising zone. And as the path gets shorter, the ellipse shrinks, letting it rapidly zero in on the best possible solution. And what about real-world vehicles? A car can't just pivot on a dime, right? That's a huge problem for planners that just connect dots. State lattice planners solve this by building paths from a whole library of pre-computed, physically possible maneuvers. Things like smooth turns and gentle curves. This makes sure the final path isn't just a series of jerky lines, but a fluid, drivable trajectory that the vehicle can actually follow in the real world. So from a simple bug just following a wall all the way to AI brains optimizing these complex paths in real time, the journey has been absolutely incredible. But it does leave us with one final thought. We've gotten really, really good at teaching robots to navigate a factory floor or a nicely mapped room. But what new algorithms, what new ways of seeing will it take to teach them to truly navigate the complex, unpredictable, and dynamic chaos of our world?